Christina. Who is the first one for the presentation? Rosita and Christina. Are they here? Rosita and Christina. I'm waiting. Rosita, hello, can you hear me?
Yes, can you hear me?
I can hear you very well.
Okay.
Are you going to be the presenter? So should I make you a presenter?
Yes, I'm just waiting for my colleague. Is Christina here? Yes, but I am going to be the presenter, yes.
Okay, so I'm gonna give you rights. Make presenter, change. So now you should be able to share your screen.
Thank you very much. All right. Wait just a second, sorry. Okay, Christina, are you here? I will call her real quick. Christina. To not waste anyone's time, maybe, I don't know, somebody that is next to us can start, and I'm waiting for my colleague that
let's wait 1 or 2 minutes.
Okay.
And after you, it's the presentation by Romagnoli and Lamesi.
Yes.
Are they ready?
Cristina,
Are they
please,
ready?
puoi collegare per favore? Stiamo già partendo. Sì, collegati. Okay, she's coming. Sorry for the delay.
And the people after you, are they ready?
Yes.
Yes.
Georgia, are you going to be the presenter? Who is going to be the presenter?
Yeah, me, Georgia.
Okay, I'll make you a presenter, so we are not going to.
Christina is arriving. I think just one couple of seconds, and she will be here.
Yeah.
Probably.
No problems. After that, we should. That's why I made Rosita a presenter, so she's gonna be ready once you have completed your presentation.
Okay.
Very nice picture, this one. This is the capital of Venezuela.
Yeah, Caracas, yes.
Caracas, have you been there?
No, I never, unfortunately.
It looks very nice. I haven't been either, so.
Yeah, we started with China, but then we had some problems with the data, and so we changed with Venezuela because we found more completed data, and felt like this was the right choice.
Okay.
Good afternoon. Can you hear me?
I can hear you very well, yes.
Okay, so we can start. Christina, can you see the screen?
Yes, thank you.
Okay.
I'm gonna start. Venezuela has the world's largest proven oil reserves at the estimated as of 2020. The country used to be one of the world's largest exporters of oil, but the oil industry saw a significant decline since its peak. In 2008, crude oil production in Venezuela was the 10th largest in the world. And the country was also the 18th largest net oil exporter in the world. And so also Venezuela is a founding member of the OECD. And the export of oil boomed in 1920 and 1935. By the end of the 30s, Venezuela had become the third.
Are you changing the slides or it's the same slide?
No, yeah, it's the same
just an
slide, and then
introduction.
we're starting.
Just an introduction, because
Okay,
we found some dummies in the 30s, and so I think it's this information is important because export of Venezuelan oil boomed between 1920 and 1935. And by the 1930, Venezuela had become the third leading oil producer in the world. So also Venezuelan oil sector currently sits at historic lows, both in terms of production and its environment impact.
Okay, let's start with the models.
Yes.
What do you think?
Okay, so this our some summary statistics about our variables. You can go on.
The information that you have, you can put it in the introduction with some, with a map or with some type of table. That would be useful. So a map, where is Venezuela, how many oil they have per capita,
Yes,
etc. You can put these whole things in the introduction. These are very important and useful.
Okay.
Yes,
Okay.
perfect. Okay.
Can go on. So these are our time series plot and color X, Y levels. About annual
So
CO2
what has
emissions.
happened to in the 50s? There is a big outlier. Eh?
Yeah, we have a big outlier in 36, 37. So we added the dummies during our model.
It looks like 1950, 1940 something, 40.
Yeah, we actually kind of it's hard to explain that because seems like really strange outliers, like if something I don't know, an incident happened or something like that. We couldn't find like really specific event to justify these outliers. We're still searching, but we think it's about of course is oil companies related.
Okay.
Christina, do you have something to add?
No, you can go on. Thank you.
Okay. Okay. So this is the time series plot and color XY of the first difference is variables. And of course, as we can see, the graph shows that is a little bit more stationary. So the variable is a little bit more, but we will, of course, do some tests later about that. And now we start with linear model.
So we started our analysis with the linear model. So our dependent variable was annual CO2 emission per capita, and our regressor was GDP per capita. And we did the y-test for heteroscedasticity. So we found that heteroscedasticity was not present. And then we did the normality of residual. So the test evidences that our residual are not distributed like normality, but our sample is big, so this doesn't constitute a problem. Also, we did the autocorrelation test, and we found that we had the autocorrelation, so we tried to implement our model adding, you can go on if you want. You can see the, I'm sorry, can you go back? Just, okay. So we also attached the image of the initial model and the actual data. So for now, the model is not as good. You can go on. So we tried to solve the autocorrelation adding a lag. And as you can see from the regressors, we have also annual CO2 emissions. And then we did again the autocorrelation test. And as we can see from the p-value output, we solved that. And also we added a dummy relevant to 37. And okay, we solved the issue of autocorrelation.
Yeah, the final solution, like we succeed in solving the autocorrelation by adding this dummy that
So
you can
in your
see.
case, autocorrelation was created by the outlier. That's it. So,
Yeah.
So basically, you could write this in your report that your
Yes.
autocorrelation issues were created by an outlier. That's it.
Okay. Perfect. And at the end, by inserting this outlier corresponding to 1947, we solved the problem of autocorrelation.
Also, we did the RMC reset tests, both for the levels and for the logarithmic variables too. And from the first RMC reset test, we found 2.2%. And so we can see that the model is not correct specified for a 5%. Also, with the logarithmic Ramsey test, we found that the p-value was even lower. So we prefer the model with the levels.
Yes, because as you suggested, Professor, if I remember correctly, we tried to put the logarithmic values, the variables, to implement the Ramsey reset test and see if it was better and the specification was getting better, but the result was not what we were expecting. So yes, it was just to show that we tried to do that.
Okay, no, that's fine. This is a logical outcome.
Okay, perfect.
Okay, you can go on. Okay, then we did some tests for parameter stability. We find that from the QLR test for structural break that we had a break in 1938.
1948.
Yeah. And then we did the Cousin test for parameter stability, and we can accept the null for 5.4%. We do not reject the null for 5.4%. And then we did the Chow test for structural break at observation 1938, and we found that we had to refase the null, so no structural break.
We found a structural break corresponding to the year 1948.
This is the same here. This is the same here. We observed the break in the very, very first graph, correct?
Yeah.
Yes, probably. Yes. Yes, you're right.
Yeah.
Okay.
If it is the same, then just make a note of it.
Okay, perfect. I'm writing this note. Okay. Do you want to go on?
Yeah.
Sorry. No. Okay.
Then we did again the LM test for autocorrelation up to order 2, and we found that a higher p-value, so the autocorrelation is not present. And okay, then we did again the reset test for specification, and the specification is is so and so. So we can accept.
You mean because it's it's 2%, 2.5?
Yeah, 2.5%.
Yeah.
Yes, we tried to make it better, but it was
Yeah, but
went better.
the logarithmic is better though. So
okay, perfect.
this is a linear with dummies, correct?
Yes, linear with dummies.
Yeah. Also, you can say that the log with the dummies gives you better Ramsey reset test results.
Okay.
Okay. So we can see the final models graph, and we found that our R squared was like 75%, and also we can see a Kaik and Schwarz criterion.
Can I ask, on the top, it's an outlier, the green spot on the top?
Yes.
Yeah,
I don't know.
exactly. This is exactly where you are. This seems like an outlier.
Yes, yes, and probably it was the probably the same also. I should check. Do you want me to find it on Gretel? If I
No,
maybe
no,
I
no.
can...
You can check it later. You don't need to do it now, but just to make sure you have identified the outlier.
All right. Okay. I will check that, of course.
Thank you. So we proceed with our analysis using the nonlinear regression model. So our dependent variable is now annual CO2 emission per capita, but our regressor are squared GDP per capita and the GDP per capita. We did the y-test for heteroscedasticity, and we found that the heteroscedasticity is not present. Then we did the test for normality of residual, and we found that the residuals are not distributed like a normal distribution. And we found that we had the autocorrelation. In particular, we find positive autocorrelation, but not negative autocorrelation. And also we did the F-test, and we can say that the model is the parameters of the regression are not zero for the variables, and we can also see the actual and fictal the annual CO2 emission versus squared GDP per capita in the graph. Hang on. So we tried to solve autocorrelation. We added a dummy relative to 1937 and 1936.
47.
Yeah. 47 and 36, yes.
47,
And
yeah, okay.
we solved the issue with autocorrelation. So as we can see, 68%. Okay, also we did the Ramsey reset test, and we found 0.26. So we can say that the model is correct specified.
Okay.
And also we did the test for parameter stability, and the QLR test for structural break says that there is a structural break because we have to reject the null. And also we did the Cousin test, 69%. And so we can say that there is no change in the parameters. And the Cho test states that at the observation 1938, the p-value is near to 0, so we have no structural break. No, we have to reject the null that says that there is no structural break, so we have a structural break.
Yeah, that was one of the years 1958 that Christina was talking about in the introduction, because something important about oil company happened, and so we can connect this with theory, of course.
Okay, that's good.
Yeah, we are searching information.
Can you go a bit faster because we need to.
Yeah,
we
okay,
need to
so
allow some time for the other presentations also.
Here we can see the final model, and we can notice the R squared, which is very, very high, 95%, and also the Akaik and Schwarz criterion are are fine.
Yes.
Okay, the logarithmic model we used as the dependent variable logarithm of annual CO2 emission per capita, and we used as a regressor constant and the logarithm of GDP per capita. We found from the white test that we had heteroscedasticity. So from this moment, we will show the test, but with robust standard errors selected for the output. Also, we did the test for normality.
Can you go to the nonlinear logarithmic model? Have you tried the nonlinear logarithmic?
The first difference you're saying?
No, the logarithmic, but with a square term.
We didn't try that.
Because here, if you stop here, you
Okay.
can see that the green line should be like a curve rather than a straight line. So if you put L GDP per capita squared, you're going to have this curve type of behavior that the blue spots are
Okay.
are pointing towards to. So maybe the nonlinear logarithmic would be the best model in your case.
Yeah,
It
because
looks to me
okay.
it looks to me from the green spots.
Okay.
Perfect. Okay, thank you very much. Yes, because we the logarithmic and the first difference that we will show now are like just going. We did the same things, of course, with the logarithmic. We solved the autocorrelation by inserting the dummy. The model is well specified as the Ramsey reset test tells us. We did kind of the same, and we didn't find any structural break for this model. In fact, we have this not strange but different QLR test, as you can see. And yes, we had really low values for Akaik and Schwarz.
Okay. And the first differences model?
This one. This one. So we did the same test as before. We found out that there is no heteroscedasticity, that errors are not normally distributed, and that we have autocorrelation, and that we also.
But here everything is insignificant.
Yes. Okay. Okay. What do you mean by insignificant?
The p-value of the constant term is 45. The p-value of LGDP per capita coefficient is 0.92.
Yes, everything. Yeah, and yes, you're right. Yeah, here everything is insignificant.
And the graph seems a bit strange also.
Okay. How do you think we can like make this better? Because I don't know. Maybe.
I don't know. It looks
Right.
there's either there is a mistake in the transformation because all the CO2 emissions are very close to zero. I don't know why.
Okay. Yeah, okay. No, and also
you have a straight line. You have a straight line, and you have all the spots on a straight line which is parallel to the axis.
Yeah.
I would focus more on the logarithmic, nonlinear logarithmic model.
Okay. Okay, for sure. Perfect. So this was actually the first difference was actually probably our best model, but because of the Akaiki and Schwarz criterion, that was really, really low. But yes, and also the confidence band plot seems kind of strange respect to the other models. So probably we have to check these again. We tried actually multiple times, and the graphs always come in this way. But I will check again and maybe do again the logarithmic first differences of the variables.
Okay.
Okay. So then we did the quantile regression model, and we compared that with the OLS output. And we found from the graph of the TOA sequence that we kind of have symmetry, and that the quantile regression follows the average response until the last quantile. So for CO2 emission that are relatively high, that we have this kind of asymmetry and a change in respect to the average response. But I think that from the values here of GDP, we can see that and we can say that so as Venezuela gets richer and richer, the CO2 emissions gets lower.
Okay.
Then we went back with the moving average model. We did the forecast, and the forecast seems to be quite nice. It's kind of similar. We dropped the last observation, and seems like the forecast is good for this model. We compared the moving average with the autoregressive model and the ARMA. And by looking at the informational criteria, we see that the best model is the MA. And then we just checked for the stationarity of the variables by doing the ADF, the Phillips-Perron test, and the KPSS. We looked for the stationarity of the variables both for annual CO2 per capita, and we found out that is non-stationary, and both for GDP per capita, and also this variable is non-stationary. So we can assert that our first OLS model was spurious. And then we did the same for the logarithmic first difference of the variables, but as we expected, we found out that they are stationary. And at the end, we did just the Capitanios test for just another unit root test, and these are our output, our results, and we stopped here. We still have to finish the project and of course check all your suggestions, but if you have any more suggestions, please tell us, and thank you very much for your time.
Thank you.
Well, the suggestion is first of all to focus on the log linear, on the nonlinear log model, and the second is to recheck the first differences, because the results looked a bit puzzling.
Okay.
And also try to format the paper. For instance, you're going to have only the linear model in one section, and then you finish with the linear model with the dummies, and then you go to the log model. You start with a simple log model, then you put the dummies. Then you go to the first differences. Then you go to the quantile, because in the presentation it was the linear model, then the log, then the linear with the dummies. No.
No, it wasn't like that. Probably because we did like all the same passages kind of for every model, but it was just the linear model, then
so you get the linear model, the linear with the dummies, then the log model, then the log with the dummies.
Yes.
Then the first differences. Okay,
yes.
This is the.
Okay.
Okay.
Perfect. Thank you very much.
That's good. That's good. Okay, thank you very much. Let me. The next one is Romagnoli, Georgia.
Yes. Good morning.
Can you?
Good afternoon, actually.
Good afternoon.
Can you
So
see
you're
the slide?
presenting with
Carla.
Yes.
Yes.
With Carla. Okay.
Okay. So let's start.
We're hearing, yes.
I leave the floor to Carla.
So good afternoon, everyone. Welcome to our presentation about CO2 emissions per capita and GDP per capita in Switzerland. Why we chose the country is actually Georgia suggested it, even though I'm the one living there. And I thought it was quite interesting because I know some things that are politically and economically happening regarding that topic in the country. For example, 2 years ago, the government wanted to update their CO2 law, but it was actually the update, which was intended to be stricter than the one now, was rejected by the population, which I found quite interesting, and now also looking at the data makes it quite interesting. So here in this first slide, we just have some corner facts and key facts about the country. So the population is just 8.5 million, so quite small, but in general, it is a quite rich country. Then maybe some historic events that we found that we tried to link later to dummies are for sure World War II and the oil crisis, which are more global ones. And then for Switzerland specifically, 1910 to 1990, where a lot of newer companies settled in Switzerland. So there was quite a big rise in GDP for that period. And then also the first introduction of the CO2 law, which was in year 2000. And we will later see why this was important. Then this little graph in the bottom, which I included, is showing the share of employed persons by economic sector. And if we just look at the pink line, which is the secondary sector, including machinery industry, engineering industry, and chemical industry, which are the biggest polluters, we can see that after the 60s, there was a big drop in that industry and more a rise in the tertiary sector, which can then also show later in the data.
If I may interrupt, the argument for a declining sector would be the argument for outsourcing activities that are environmentally costly, correct?
Exactly.
Okay.
Can we move one slide forward, Giorgia? Yeah. These are summary statistics just to give a general base. We included just the level 1 and then the growth rate because later we saw that those will be the main ones that are quite relevant. And then in the next slide, we can see the general figures. So for the levels, we see in annual CO2 emissions quite an upward trend. But in the beginning, it was a bit volatile because of the world wars. And then it rose a lot when the industrial era kind of boomed in Switzerland. And then it balanced out throughout the 90s. And then after 2000, it started dropping again. Whereas for the GDP, we can just see a rising trend. And then the XY plot shows kind of the same thing.
Okay, you have the filter there, which is very nice.
Yeah, we include the filter to understand the smooth path of the annual CO2 emission and to understand better how it's going. Then how we proceed in our analysis was to try to run all the main models and try to fix them for the specification test. So of course, heteroscedasticity, autocorrelation, and normative residuals. Here we start with a linear model. From the graph, the first thing that we notice is that, of course, Switzerland is one of the richest countries in Europe, and indeed we can start to see the shape of the Kuznets environmental curve, understanding that nowadays the country is experimenting the downsloping part of the curve, in which the annual CO2 emission decrease, even if the richness of the country, and so the GDP increase or is stable. But so we understood that the country is in this phase. Here we can see that we had a problem of heteroscedasticity, autocorrelation, while the residual test show normal distribution. For this reason, we try to fix it, including lag both in the dependent and in the explanatory variables. How we can see from the graph, it actually improve a lot our linear model. Indeed, we adjust for heteroscedasticity and also for autocorrelation, even how we can see in the correlogram graph, where there are few outliers. respect to the previous model. And we also, of course, tested for parameter stability. And as Carla said before, doing all our analysis and models, we try to link the structural break in our observation with historical event in order to try to find, of course, a reason for these kind of structural breaks. As we are going to see even in the next slides. Then we have the logarithm model. In this case, we also we saw that all the problems were present with this model. Indeed, we had heteroscedasticity, autocorrelation, and of course, the residuals were not normally distributed. So we proceed as before, including some lags. And how we can see here, including the one log of the dependent variables, again, of course, the data from are, of course, more in line with the actual observation. So we can see from this graph. Also, autocorrelation has been solved, and as before, the parameter stability tests have been run in order to understand where and having an idea about the stability of our parameters over time. For linear and log, we also run a quantile regression. We decide to include these two graphs in order to make a comparison between quantile regression for the log model and the linear. Indeed, while...
This is very good.
Okay, thank you. While in the log model, we see that the quantile regression is inside the confidence interval of the OLS.
Sorry, give me just 1 minute.
Yeah.
Yes, you can continue. Sorry.
Okay. So I was saying that, oh, no, sorry. Where is it? Saying that so while the quantile regression for the log model is fall inside the confidence interval of the OLS regressor, sorry, okay, we found that the quantile regression for the linear model was show quite an asymmetry, especially after the middle quantile, so after 0.5, where we can see that the quantile regression is fitting better our data with a higher confidence interval at the end. I don't know if you can see, but the gray area is
I can see, and the comment here is that there is asymmetry in the linear model, but there is no asymmetry in the log model.
Yes. Sorry, I don't know why.
So that's the basic conclusion. Okay.
Mm-hmm. Exactly, and so we understood that, especially in the last quantile where the CO2 emission level were very high, the GDP per capita was not very specific, precise in explaining the change in our dependent variable. Then we proceed with the nonlinear model, and in this slide we decided to include also the regression residual graph because it was very useful for us to understand where we found our peak that we use in the improved linear model to correct autocorrelation because we discovered that autocorrelation was caused by these two outliers. Indeed, as we can see in the improved non-linear model, we include one lag of the dependent variables at these two dummies, 9045 and 9073. From the graph of actual and fitted, we can see that they are quite symmetry. And we also test, in this case, the Kusum test using not a single dummy to understand the structural break, but a range of year, which was between 1987 and 2004. Going on, we have the first difference model. Even in this case, it was quite good. We do not have autocorrelation problem, but we saw this huge shock, which of course are linked to the Second World War. So the dramatic decrease of CO2 emission in 1945 and then increase in 1946. So we use this two shock in our dummies to improve the model. Indeed, here you can see the improved model with not heteroscedasticity. We solve autocorrelation, and we also, as usual, run our parameter stability. At the end of this part of our analysis, we did this comparative table. Here you can see all the main measurements to compare
this
our.
This is a very, very good table. Well done.
Thank you. So we try to insert all the main measures. Of course, we we focus on the reset value, and as you can see, we underline the improved log model and improved first difference model because they are the only two that allows us to fail to reject the null, and so the model well adequate specified. But how we are going to see in the next slides, the improved log model is a spurious model. And so we think that this high R square could be caused by the spurious model, while the improved first difference model involved two not spurious variables, and so even this model we think that it could be quite reliable. And then I'll leave the floor to Carla.
Yeah, but we have 2 more minutes.
Okay.
We'll just rush through the rest. So because we have time series, we also ran an ARMA model with lags of 2, and we saw that autocorrelation is solved and the model is not too bad, but also I tried forecasting and it didn't work quite well. So I would leave that model because I think the first difference model, the improved one, is a lot better.
Include it in the project, but say it doesn't work very well.
Yeah.
Okay.
And then we just ran some tests for unit roots testing because we assumed that there would be non-stationarity and that for the growth rates there would be stationarity. And as we see in the next slide, actually our assumptions were correct, that for the growth rates there is stationarity and for the level of variables there is non-stationarity. Then we checked with all the tests and came more or less.
Very good tables.
And then as for the last tests, we also ran co-integration. There is in fact no co-integration for the level variables. And the last thing we did was a vector autoregression to test for causality tests, which showed a bit ambivalent results. We did not really know what to conclude out of this because it shows, for example, on the right side, we see that at a 1% level, we can say that there is causality at 5 and 10%, but not at 1%. And then also only for
here you're finding that CO2 emissions, GDP doesn't Granger cause CO2 emissions at the 10 point 9%, which is really marginal.
Mhm.
So if you had a significant level of 11%, you will say that GDP is affecting CO2 emissions. So this is a marginal result. Just make a comment of it.
Okay.
And now whether CO2 emissions are greater causing GDP at the 5%, it does, because the p-value is 3.2. So if you are going to be relatively generous in terms of the p-values, what you're finding is a bilateral relationship. So it's both ways.
Mhm.
So this is what you could say.
Okay. Then that is what we have done. And for now, we would just work.
You have done a very, very, very good job. Well done.
Thank you.
Thank you.
Very good job and very, very nice, very professional slides.
Thank you.
Very good. The next presentation is Petra.
Yes, I'll share the screen.
We're hearing Petra. Please use 15 minutes and not more than 15 minutes, please. Okay. Can you hear me? I cannot hear you. I cannot hear
Really,
you.
we cannot hear you.
Ah, you cannot hear me.
No, because should be Rebecca, the one who's gonna present the first part. So she's
I
gonna.
can hear you. I can hear you now.
Yeah, I know,
Petra.
but we cannot
Sorry,
hear
forgot to
you.
turn
Okay,
on my
great.
microphone, sorry.
Okay,
Perfect.
Rebecca, please share the slides.
Yeah, sure. Rebe, I cannot hear you.
Rebecca, we cannot hear and we cannot see in slides.
Petra is sharing the slides.
Yeah, but I were you talking? Because I couldn't hear you.
No, I can't see the slides though.
Okay, I'll try again. Working. Can you see it now?
No. Ah, yes, now. Yes, we can see
Okay.
now.
Great.
Okay, just try to be on time, please.
Yeah, sorry.
Okay, so for our project, we decided to study the relationship between CO2 emissions per capita and GDP per capita of South Africa. We thought it was interesting to look at a country in Africa which has the third highest GDP as of this date, and probably in the past had one of the highest ones. And we thought it was interesting because South Africa has historically had an industry and economy based on its natural and environmental endowments, such as mining of diamonds and gold. And we thought it would be really interesting to see if they are moving towards a greener economy or if they are still relying on these industries. So we started our investigation by looking at by plotting our variables over time and doing a fitted graph, and we can see that just immediately they're not really decreasing. So it seems like the economy is still quite industry heavy. Then we also did a color XY of our levels. And we can see that there's a drop around the 1980s, which is probably due to all the political and social issues surrounding apartheid that were happening in South Africa at the time. We performed the same graphs for our first difference variables. And we can see that here, except for the initial years, the values gather around the mean quite strictly. We can see that through all these graphs, I think, that they're all clustered around the mean value. And after this, we looked at the summary statistics for all our variables.
Yeah, sorry. Not working.
Oh.
Oh. not working at all. I don't know why we're having so much.
So we looked at summary statistics, and we can see that the graphs are supported also in the output of the summary statistics. In fact, the standard deviation around the mean for our growth rates is really small, really low. And after this general outlook on our variables, we decided to start performing different models, looking at different models. So we start with a linear model. Is it? Okay, and we can see that immediately our p-values tell us that our coefficients are statistically significant. We can see that we have normality in our residuals just right off the bat, but we see that we have heteroskedasticity, we have autocorrelation, and so we need to try to fix our model. We did so by immediately flagging robust standard errors, so we get rid of the heteroskedasticity, and we also added a lag of the dependent variable, and we can see that by doing this, we get rid of our autocorrelation, which was really good. Then we did different tests. We did a reset test to see if the linear model was a good specification, was a good appropriate functional form, and we can see that based on the p-value, we would have to reject that hypothesis and say that it is not a good functional form. Then we did a Kazam test, QLR test, and Chow test to see if there was a structural break and at which year we could see a structural break. And we can see that the QLR tells us that it might be appropriate to insert a break in 1908. So then we move on to our nonlinear model. Again, we can see that all our coefficients are statistically significant, but here all our tests are rejected. So we don't have normality, we have heteroskedasticity, and we have autocorrelation. To fix it, we have done the same things. We have included a lag of the dependent variable, and we have flagged robust standard errors. We can see that, unfortunately, we are not able to get rid of the non-normality of our residuals. We tried to do this also by adding dummies. And while the dummies were statistically significant, unfortunately, they gave us a worse model, both in terms of adjusted R-squared and Akaike criterion. So we decided to use the model that didn't have dummies. So we fixed the heteroskedasticity by flagging robust standard errors. We fixed the autocorrelation by using a lagged value. And we can see that here our reset value is positive, so we can accept the null here, and we can say that our nonlinear model is a good functional, it's an appropriate functional form for our data. We can see that our QLR gives us a really small p-value, so we have to reject the null. And yes, same with the Chow. Then we did a logarithmic model. Again, we have pretty much the same picture. Our coefficients
You have five minutes.
Are statistically significant. Again, we have all of the tests are rejected. So we fix this model again by adding lagged values and flagging robust standard errors. And these are our p-values. You can see that it's interesting that the graphs kind of plateau and it doesn't increase, peak, and then decrease as we would expect to see from a Kuznets curve. I did the same thing for the first difference model. So again, coefficients are significant. All of our tests are rejected. So we fix again through lagged values and robust standard errors. And we see that we can always fix the autocorrelation, but we are not able to fix the normality. Then our reset value was also was accepted. So we can say that also in this model could be an appropriate functional form. Next slide. Then we did a QR test, and we did the test for both the levels and the logarithmic model, but we've only included
quantile regression, not the test. It's a regression.
Sorry. We can see here that the quantile regression is almost completely within the confidence bounds, except for the relatively high values. So we can say that OLS doesn't really capture what happens at relatively high values when it comes to our levels. Then we compared also the median, the middle quartile for our quartile regression, and the coefficient for our OLS, and we can see that they're quite close, which would seem to support that OLS captures the average value quite well.
Okay.
Okay, so looking at also the results of our moving average, so we performed some time series and the results from our moving average estimates for the first differences model. We can see that all the coefficients are statistically significant. We also performed the forecast by first modifying our number of observations and reduce them in order to be able to perform a real forecast and then compare it. But as we can see from our graph, the forecasting doesn't follow our data too closely. We also perform an autoregressive estimate and a normal one using both the moving average and the autoregressive. We compare them by looking at the information criteria, and in this case, we decided to take into account the archaic and the Schwarz. Both of them tell us that our best model between the three is the mixed one. And even if we can self-serve some correlation between the residuals, we can see from the graph. So more precisely, we have at least 5 points that are correlated. We then tested all our variables to determine if they had the structural breaks. Before doing that, we observed their behavior to a time series graph. From there, we can see and we could say that the only two variables that might be stationary are our first differences, since they seem to be concentrated around the mean, while all the others have a clear increasing trend. After testing them with the augmented bipolar, the Phillips-Perron, and the KPSS test, we can confirm that only the first differences variable are stationary, and according to the Phillips-Perron test, also the logarithmic variable CO2. So we also conduct a Capitani's test to understand if our first difference could be stationary after including a number of breaks. In this case, we decided to include 3 breaks each. So the test turned out that our first difference CO2, we could insert 3 breaks at year 1899, 1932, and 1916. And while for our GDP, we could insert 3 structural breaks at 1915 and 1993. So if we follow this suggestion, we can actually rely on the stationarity of our variable. In order to improve our model, we took a look at the co-integration of our variables. And so we can clearly see from our Aldrich-Prescott graph that our levels seem to have a strong positive trend as they are moving in the same direction, while our log variables are both increasing, but at different pace, and don't seem to have a trend as strong as the one with our levels. Also, in our first different variables, as we would expect, there is no evidence of a trend. So as most values gather around the mean. We conduct also a co-integration test for all 4 models, even if we're almost certain that our first difference is stationary. So as we can see, none of them show co-integration. Since to be co-integrated, the bipolar test must not be rejected for the variables and must be rejected for the residual. So here we can see that the p-value highlighted in red are the ones that do not allow the models to be co-integrated. And given that our first difference variable is stationary, we decided to run a causality test on them. So after trying various number of flags, we decided to use
the causality test is a Granger causality, not Engel. It's only it's called only Granger causality.
Okay.
And you found some causality here. Okay.
Okay. we decided to look for the 10 likes. And yes, by studying the F-test, we can determine if there's a causal relationship. It turned out that there is a causal relationship between both all the lag values and of CO2 emission and CO2 emission. The same for all the lag value of GDP and GDP. Yeah, we can see some causality. And the last one is our graph where we trying to, nothing is working, I don't know why. Okay, sorry. We run sorry, but it's not working. We also decided to undertake the catch-up, and by looking at the graph, we can see that how our coefficient varies in time. So this graph isn't exactly comforting, as it seems that our coefficient is constant with a slight but very slow decrease. So this could mean that South Africa has not yet disentangled its economic prosperity from its emission. And the last one, we tried to build a model, build a graph to identify our best model. So we compare all the fixed model, and we also had some information criteria, and we look also from specificity autocorrelation.
Very good presentation.
Thank you. Okay. Sorry for your
very good. Yeah, very good presentation. Try to put all things in the project, and you have done a very good work. Okay.
Thank you.
Thank you.
Shall we move to Salvatore? And Salvatore, please, 15 minutes, not more than that.
Can you see and listen to me?
Yes, I can see you, but I cannot see the presentation, but please be on time.
Yeah.
15 minutes.
Yeah, I'm trying to show.
To interrupt if... Okay, we're hearing Ataul.
I'm starting. So we are presenting this work on Portugal. We have to remember that Portugal was a dictatorship, and also that was it had a colonial empire that lasted until the Second World War. After the Second World War, and so let's move to more statistical things. We have as first thing the colored XY plot, and we can see that there is an increasing relationship between GDP and emissions, in particular until the 80s. Then we have this decreasing trend, and we're gonna describe the meaning of it. And maybe
did you do the filter?
What? The filter? What?
Yes, you could do. You can do the filter if you want to also.
Okay, yeah, we're gonna put it in the project.
Yes.
And the decreasing trend, maybe it means that they also started to delocalize, and but we have to mention that Portugal is one of the, let's say, most underdeveloped countries in Europe, and was also part of the peak. So Portugal, Italy, and Greece, Ireland. So it would be a relevant matter to also analyze the question of the sovereign debt during the last recession. Then we have the summary statistics for all our variables, both differential variables and logs. Can you hear me?
Yes, I can hear you very well.
Okay. We have the time series plots. We can already suggest that there is no stationarity for normal variables and for logs, but stationarity, then we will test it. Of course, we have the slides on it, and stationarity is only present for different values and log differences. And also, we note that there are some outliers in the last four models. So the difference model, the difference variables, and the log difference. So let's start with the linear model. We have all the problems that one could have experienced. So we have no test that went good. GDP is significant based on its p-value, and also we have the confidence interval for its value. The only test that we passed. So that was a success, was the Chow test for the 1932. And around that year, Salazar became prime minister. So it's the beginning of the dictatorship in Portugal and of the fascism, let's say. We have we have autocorrelation, and the model is not correctly specified, as we can understand from the relevant test for these topics. There is no stability in the parameters, as we can understand from the Kusum test. And to correct this model, we have added two legs of the dependent variables, so of the CO2 emissions, and two dummies. And the reason for these two dummies, the first one for the 89, is that during that year, there is the start of the privatization process. So banks and major industries of the country started to become private for the first time. And in the 2003, instead, we have the only one recession in Europe, even if it's not so relevant in terms of percentage impact on the economy. Almost 1%, so yes, it's relevant. And this amended model, we have non-normality still. The Chow test still not valid, but parameters are now valid. There is no autocorrelation. The reset test is not valid also in this case. And so our suggestion is that maybe we need more legs and more dummies, but we have to understand it in a second moment, of course. These are some other graphs. This time we have the stability of our coefficients, as we can see from the graph of the Kusum test. And we can start to see the beginning maybe of a Kuznets curve in the last years. But that's just something like that we can further explore with the nonlinear model, as we are going to see. We have the quantile regression. In general, the OLS line is inside the interval that we have for the quantile regression, except for the values in the tails of the series. We used 5 quantiles, of course, and in order to understand in fact, if there are significant changes between the impact of GDP and CO2 emissions. The most important quantile is the first one, as we can understand from its coefficient. And in fact, it's a 2% 2% impact on CO2 emissions. Logarithmic model, all tests failed, of course, and we have stationarity. At least there is stationarity, and those are some of the graphs.
Stationarity. How do you know the stationarity?
We tested for it. We're gonna see it later. No, sorry, I did a mistake. We have no stationarity. There was a note. Yes. There was a note that I had to delete. Anyway, we amended also this model, and this is the result. All tests passed except for normality and reset test. And there is, as we can elicit from the graph, a decreasing marginal impact of the log of GDP on the emissions of CO2. So it's a good sign for the correlation between these two variables. And also we have stability in the coefficients. And on the left, we can see the confidence interval bands for annual CO2 emissions on the 95% confidence interval. Then we have our nonlinear model. We can already notice that the square variable of GDP has a negative impact on CO2 emissions, as there is.
But it's not significant.
It's not significant, so we are not considering it. And we try to amend it as well. And we added a leg of dependent variable and 2 dummies. So
this looks good. This looks good.
Yeah.
This one.
Yeah, this one is best.
You have
so
5
far.
minutes.
Yeah, this is the best so far, and so we can see that the graph is now trying to approach this kind of Kuznets curve that is more visible, but still we have no a peak for the emissions. This is amended. We have stability. This is the first difference model. We have homoscedasticity and no structural breaks and a good specification, as we can understand from the relevant test. So the RESD test for specification, and also the Chow test and the QLR test. Autocorrelation is still present. We try to model this model in order to correct these problems. 2 legs of UI and 2 dummies were added. So now we have no autocorrelation and stability in the coefficients. But we don't have the normality in this model as in the previous ones. But still, it's well specified, but the Kuznets curve is invisible, as we can note from the actual versus fitted graph. The cushion test still shows that there is stability in the coefficients. And this is the part about dynamic models that Osman is going to explain.
Okay, thank you. We have estimated 3 models. One is AR model and another is MA model. And we have amended both types of model in a model. And we can see that there is a lower AKI value in ARMA model. So based on our estimation, this is the best model. We have done the forecasting based on ARMA model, for 4 years. And our forecasting is very much aligned with the previous data sets of CO2 emission. So keeps go on. Next slide. This is the summarized result. Which model is the best? And
very
you
good
can
table.
see. Yes, we can see. Next, we have done unit 2 test for annual CO2 emission and GDP per capita, and the fast difference of both variables. And we did the 2 types of test. One is ADF test, and another is Phillips-Feron test. And we have observed that in ADF test, annual CO2 emission and CO2 emission and GDP per capita is not stationary, but in case of fast difference variable, we found that the variables are stationary. But the interesting fact that in ADF test of GDP per capita, of fast difference variable is not stationary. But in Phillips-Feron test, we found that GDP per capita at fast difference is stationary. Next, please. This is the summarized result, and we also did the Capitanese structural break test, and we found that at fast difference level, GDP per capita has 3 structural breaks: 1919, 1959, and 1985. And for CO2 emission, we have 3 more structural breaks: 1897, 1998, and 1943. Okay, so in next slide, we can see that the structural break test and also the test of co-integration. There are 4 steps of co-integration test. At first step, we can see that there is a stationarity test of logged variable of CO2 emission per capita, and in the next step, we can find that. Please go. In the next step, we can find that stationarity test of GDP per capita. And in both cases, we do not find that they are stationary. And in the third step, we found co-integrating regression. And in the fourth step, we estimate the residual stationarity of residual term, and we found that it is not stationary, so we can conclude that there is no co-integration. That means no long-run relationship between GDP per capita and CO2 emission. And in next, this is important for co-integration test because we need the same trending variable to test the co-integration test. So in next slide, we estimated the VAR model. VAR model based on the lag selection criteria of 6 lag according to the Akaiki information, and we found that there is a Ganser causal relationship from unidirectional Ganser causal relationship from GDP per capita to CO2 emission, and otherwise it's not valid from CO2 emission and CO2 emission to GDP per capita. And this is another estimation of VAR model, because you can see that there are two criteria, Bayesian information criteria and Hannan-Quinn criterion. Based on these two criterion, we have to select on lag. So we re-estimated these models again by selecting on lag. But as you suggested in the lectures, that we have to select lags based on Akaiki information. So previous one was the that explanation, and finally
you have to go to finally, because we're running out of time.
Yes, and finally we did the Kedval's test, and we found that there is a gradual continuous decreasing trend of parameters until the 1920, and in recent times these parameters are very much stable. Thank you.
Very good presentation. Well done.
Okay, welcome.
Any questions for me?
Yeah. Can I ask if you can give some tips about the improvement of the models, and which model?
The tables that summarize the results that you saw in previous presentations, and some of the tables that you have done yourself for unit roots, you can do it for all your, for example, something like this is very useful for the reader. So create summary tables in Excel instead of copying and paste everything from Gretel. That's the only tip you can do. The other thing is, when you do co-integration, you can try and see if you take into account structural breaks, the co-integration is there or not. But this is something you have to work on your own if you want to do something further. Okay.
But can I ask one last thing, if possible?
Yes, the only problem is we're taking the time of the next group. That's the problem. But
okay.
Yes.
Eventually, I will email you eventually. Okay.
No, tell me now, so everybody can hear it. But
if we want to find the correct order of the dynamic models, how can we do that? Because I've seen that there is this kind of let's say technique in which we have to look at the ACF and PACF graphs and then select the lags according to that. But I've read that this is not possible.
This is the old technique. Now we're looking at the Akaiki and the Schwarz.
Okay. So there is a new and old. Okay.
Yeah. So what you have done is the correct thing.
Okay. Perfect.
Okay. In fact, if you go to Gretel, there is an ARIMA selection add-in function package that is doing this automatically for you. Okay. It's called Auto ARIMA.
Auto ARIMA. Perfect.
Okay.
Thank you.
Okay.
So the next one.
Can you hear me?
Yes.
I'm trying to share the screen.
Okay. I thought Pietro wanted to be the presenter.
Yes. Just 1 minute.
Okay, you can start presenting it. Please be careful with the time.
Yes, but I cannot see the presentation.
You are a presenter, but
I don't see the presentation.
yeah. Who is going to?
I'm here.
Pietro.
You can see?
No, I cannot see anything.
I think I'm sharing.
Did you press the button share on the top right?
Yes, but
Press it again.
you can see?
I cannot see anything.
I'm
No,
sorry.
I can try if you make me like a presenter. I will
You
try.
are, Simone, you are a presenter as well.
Ah, perfect. So I try to share my screen now.
And
Can you
please,
hear everything?
I can hear you very well.
Okay. Okay. So presentation. It's because I'm outside, so
You are in a very nice place.
thank you. It's the seaside in Cesena.
It
Sorry
looks
for
very
the.
nice.
Okay, one sec. Condividi. Oh. Now you should see.
Yes, now I
Okay.
can see, but Simone, you have to be fast because
Yes.
now you
Yes.
have like 10 minutes.
So basically, we did all
So
the
please
tests.
just say the basic stuff.
Yes, we planned the presentation about saying the basic stuff. Actually, we did the exactly same tests of our colleagues: the linear, the logarithmic, the square, and the first difference models. They all had autocorrelation, heteroscedasticity, and non-normality of residuals. So first we tried to correct autocorrelation from the four models, and then we tried to spot heteroscedasticity, and we did the Ramsey test. So to start, this is the amended model in the linear model. The RESD test does not reject a wrong specification, and this means that the autoregressive, in our opinion, that our regressive model is a nice specification, but the linear is wrong. Indeed, before correcting for everything, the RESD test was not was rejecting the correct specification. So we won't go for a linear model here, apart if for an autoregressive one.
Can I see the log model?
Yes, this is the log model. It is actually we try two different ways to correct autocorrelation. The one on the left is the only model we used dummies because we realized that it was better, in our opinion, to use less variable if possible, but still to correct autocorrelation. It was better to use the an autoregressive model of order 2 on the right. So even if the dummies are statistically significant, they just gave us a higher p-value to do not reject. But actually, we thought this could be like not so important to improve the model because we just added 2 legs and it was okay like this. And something interesting about the logarithmic is that as Pietro will tell you, the log variable of annual CO2 is stationary and the log of GDP is not. So maybe we can still use a OLS model to not and avoid still having a spurious regression.
Can we move to the next model?
Yeah, however, we really like the squared model, which is the one on the left. I will tell you in short what we did on the right, because, sorry, as you know, the environmental closeness curve has a quadratic shape. So we correct it by adding the first and fifth log of the dependent variable. All coefficients are statistically significant, which is very good and different from the previous model, the logarithmic one. And it is negative, this coefficient, and this one is positive, which is in line with the theory. But still, the GDP and the square are not stationary variables, so we might have a spurious regression. We thought about using the square of the log, but later, Professor, we will ask you about this because we are not sure how to interpret it. On the right, we just tried to include the shock of log 1, and actually it worked as well. So we could say we have more an autoregressive approach on the left, and we try to correct for shocks on the right. But the best model, in our opinion, was of course, the first difference one, because we remove autocorrelation by taking the log of order 1 plus we remove the dependency because we do first differences. And yeah, the RESD test for specification says it's not a proper model. Maybe in our opinion, because the log difference of GDP is not does not explain the causal relationship, even if it's statistically significant. But Pietro will talk about this in the causality test we will do later. Thank you. And we also did the quantile regression, but yeah, basically we see that there are strike differences between low values and high values. So yeah, we should use or a quantile regression or maybe estimate 2 different regressions. Thank you. Pietro, you can go.
Yes, here we have the time series graph of the CO2 emission and GDP that highlight that these 2 variables are non-stationary because they are trending over the analysis period. To solve
You have 4 minutes, huh?
Yes, to solve this problem, we have computed the first differences of the logs, and then we have obtained the growth rate that are stationary, as evidenced by the graphs. Then we have the correlogram, which shows that for the growth rate of annual CO2 emissions, the more significant autocorrelation coefficient is that of order 1, while for the growth rate of GDP is that of order 10. You can go ahead. Then to solve the problem of the correlation, we have computed time series models. The best models are the moving average with lag of first order and the autoregressive model with lags of first order. We have computed the forecast for both models because the Akaike information criterion and the Schwarzman Bayesian were very similar. So we have obtained forecasts that are quite similar with respect to the real data and that are included inside the 95% confidence interval. So we are quite happy about this. You can go ahead, thanks. Then we have done all the unit roots and stationarity test, and from this table we can see that they are all in line because we obtained the correct result for all of these tests. Go. Here we have also done the co-integration for the variables in levels that show that both the variables and the residuals are non-stationary, which means that co-integration is not present. And then we have done the co-integration test both for the logs and for the growth rates, but co-integration is still not present. Then we have the last slide. At the end of our analysis, we have done the VAR models to test the causality, and this finding shows that the variables analyzed are not connected by a causality relationship because we can see that each variable is affected by lagged values of itself and not from lagged values of the other variable. And it's a short summary of all our project.
Okay. But in the presentation, in the project, you're going to put more graphs, you're going to explain things, and you can create tables like the ones you had in the end, which were very good.
Yes.
Other questions?
May I ask you something? Yes.
Yeah.
Because we thought about using the square of the log, but in the model, we don't know how to interpret the parameter, the coefficient of this variable.
It's like, it's like the environmental Kuznets curve.
So we can use like the square of the GDP, like the log of GDP, and take the square of this and use it?
Yes.
Okay, because yeah, we don't know how to say that, like the coefficient interpretation about this, but
You can use
but
it.
it worked. It worked, but yeah, we couldn't express.
Okay. Other questions?
No, thanks.
Okay, so try to create nice graphs as well. Okay, Nihat, can you present?
Yes, can you hear me?
Yes, I can hear you very well, and please be aware of the time, please.
Yes.
So
Okay.
you have 15 minutes.
Oops. Can you see my screen?
No?
Now?
Now we can see the calendar. Yeah. Yes, the
Okay.
PowerPoint.
Okay.
Singapore.
Yes.
Please be aware of the time.
Yes. Okay, so my study case is on Singapore, and I want to know the relationship between CO2 emissions per capita and GDP per capita. Actually, I'm just going to skip the introduction. I just want to mention that in the past, petroleum and other liquids represented 86% of Singapore's primary energy consumption, and natural gas was only 13%. And then now it's natural gas represents 95% of Singapore's energy consumption. It's important for later to understand the fluctuations. So I've got 69 observations. It's not a lot, but the country is quite young. And if we look at the correlation matrix, we see the correlation between the two variables is positive, and this correlation is statistically significant. So it can mean that as Singapore becomes richer, the more it produces CO2 emissions. And if you look at the scatter plot, we can say that the start of the industrialization, Singapore polluted more, but as it becomes richer, it tends to produce less CO2 emissions. If you look at the time series plot, just to understand the variations, in 65, Singapore split from the Malaysian Federation, and it experienced rapid economic growth. And yes, so the relationship was positive. And then between 2004 and 2007, Singapore was one of the strongest economies in the region. But then in 2009, Singapore pledged to reduce its CO2 emissions. And it's at this time that the country decided to switch to natural gas as a primary energy consumption, which explains the big drop here. Yes, but this strategy is now, I think, it reached its limit, and they should find new ways to reduce their CO2 emissions. Because
you can add a filter there to highlight this by using a filter.
Okay. Yeah, so basically the drop in CO2 emissions is just because they switched to natural gas, and it's not because they use new cleaner energy. Okay, let's start with the linear model. I run the OLS regression, and the R squared of the regression model is 19%, which reveals that 90% of the variation of annual CO2 emissions per capita can be explained by variations of GDP capita. And if you look at the T ratio and p-value, we can reject the null hypothesis. Yeah, it's statistically significant.
Yes, and then I did the diagnostic test, and with the normality test, the p-value is quite low. So we reject the null hypothesis that the error terms are normally distributed, and then the white test, the p-value is not statistically significant. So in this case, we do not reject the null hypothesis. So heterodiscity is not present. And then for both autocorrelation tests, the Durbin-Watson statistic test, there is positive correlation. And for the autocorrelation, for the Broich-Goldfrey test, there is autocorrelation. And then for the Ramsey reset test, the linear model is not a good fit. And then to test the parameter stability, for the Chow test, we reject the null hypothesis. The parameters are not stable over time. And for the COSM test, there is instability in the model. And for the QLR test, we reject the null and the parameters are unstable. And the potential year for a break is 1980. And just to correct the autocorrelation, I added one lag of the dependent variable and dummies of these years. And the lagged values of the dependent variable and the outliers are statistically significant. And the p-value of the autocorrelation is at 0.56, which is not statistically significant. So we don't reject the null, which means there is no autocorrelation. And then for the logarithmic model, the R-squared of this regression is around 54%, which reveals that 54% of the data fits the regression model. And the T ratio and p-value, we can reject the null hypothesis, and it's statistically significant. And yeah. For the diagnostic test, for the normality test, in this case, we reject the null hypothesis. The error terms are not normally distributed. For the white test, the p-value is at 0.36, which is not statistically significant. So in this case, we do not reject the null hypothesis. And then for the autocorrelation, for the Durbin-Watson statistic, we have positive correlation and autocorrelation. And then for the Broich-Goldfrey test, there is autocorrelation. And then for the Ramsey reset test, the linear model is not a good fit. And to test the parameter stability, the Chow test, we reject the null hypothesis, and the parameters are not stable over time. And for the consume test, there is instability in the model. Here too, we can see. And then for the QRL test, we reject the null, and the parameters are unstable. And the potential year of a break is 92. Okay, so here I added one lag of the dependent variable, and the lagged value was significantly statistically significant, and where we can see the autocorrelation. We don't reject the null hypothesis, which means there is no autocorrelation. Next is the non-linear model. So maybe the relationship between annual CO2 emissions per capita and GDP per capita is non-linear. So now we add the square of the square of GDP per capita. And yeah, the R squared for this regression model is about 69%, which reveals that 69% of the data fits the regression model. The T ratio and P value are significant. Yeah, the constant term is significant at 5% level of significance, and both beta 1, beta 2 are statistically significant at 1% level of significance. And yeah, if we see the graph, we can see that as the country gets richer, we can observe that the CO2 emissions per capita declines. And for the diagnostic test, the normality test, the p-value is not statistically significant. In this case, we don't reject the null hypothesis. So the error terms are normally distributed. The white test, the p-value is 0.12, which is not statistically significant. So in this case, we do not reject the null. And then for the autocorrelation with the Durbin-Watson test, we have positive autocorrelation. And then for the Godfrey test, we reject the null, and there is autocorrelation. So yeah, this means we have Rank's estimates. And then for the Ramsey test for specification, we reject the null. And yeah, the nonlinear model is not a good fit. And to test the parameters, the stability, for the Chow test, we reject the null hypothesis. The parameters are not stable during the entire period. And then for the consume test, p-value indicates that there is no stability in this model too. And the QLR test, we reject the null. And yeah, the potential year would be 1971. And to correct the autocorrelation, I added one lag of the dependent variable and the dummy variables of these years. And they are all statistically significant. And then if you see the autocorrelation, the p-value is, yeah, we don't reject the null, which means there is no autocorrelation. Then we ask ourselves, like, what happens when CO2 emissions per capita are relatively low or high? And so, yeah, so the blue line is the OLS, which is the average response.
So the relationship is symmetric. You don't see
Yes.
any
Exactly.
significant asymmetry here. Yes.
Yes. It seems like the average response is a good approximation of what's happening yeah, when CO2 emissions are low and when CO2 emissions are high. And then I added the logs. I did it with the logs. And on average, if GDP per capita increases by 1%, the increase of CO2 emissions is by 60%. And the asymmetrical response indicates that when CO2 emissions are low, basically when Singapore was not a wealthy state, a 1% increase in GDP per capita meant 70% increase in CO2 emissions. But when CO2 emissions are high, aka when Singapore became rich, an increase in GDP per capita by 1% meant by 1% increase CO2 emissions per capita by 30%, 0.30%. So there is an asymmetric response here.
You've got 2 minutes.
Yes, I'm actually done, because when I did my first difference model, my alpha and beta were not statistically significant, so I couldn't really work with it. but I'm not. I have to find out.
Okay, so you have to do the autoregressive and the unit roots.
It's what? I didn't hear.
The autoregressive, moving average, and the unit root models.
Yes.
Yes, you haven't done this part.
No,
Okay.
no. I need to do the time series models.
Yes, you need to do the time series. Okay,
Yes,
very
yes.
good.
That's pretty.
Okay, very good, very good. Thank you very much. Ilaria is here. Ilaria, Eski,
Yes.
can you start presenting?
Yeah,
You're
sure.
together.
Yeah. Okay.
So
So-
you met in one place. Very nice. Okay.
Yeah. So we chose Turkey as the country that we want to analyze, and we're group 28.
Please be aware of the time, please.
Yeah. So we started with the time series plot, and we can see from the graphs that CO2 and GDP are directly correlated because they increase together during the years. And also we can see some fluctuation in the logarithmic graph because they're around the 1946 because of the war. So that's the only thing that we noticed in this graph. And then if we go to the color
XY plots of linear and logarithmic models. So we can see that correlation was positive between GDP and CO2 per capita, but lately we can see some negative, it's getting negative for some years, but then trend went back to positive again. It can be also explained by Turkey, like not being in European Union, so they're not sometimes following the EU directives.
And then we did a correlation for the linear model, and we can see that the our variables are highly correlated because also we reject the null hypothesis. So because our p-value is 0, and the correlation is statistically significant in this case for Turkey, for the data that we analyzed. And
okay, so here are we have some summary statistics.
Yeah.
We think we can analyze the median values instead of means because they're not influenced by outliers.
Mm-hmm.
Do not forget to do the filters also.
Yes,
yeah,
the filter data
on the final
in the Word document in the last. Yeah. And then for the linear model, we analyzed and we put the outputs in the slide. So we tried to fix the Ramsey test, but we still couldn't fix it, and it happened in other models too. We added lags and dummies, but still it was not well specified. But in this case, we were able to fix the autocorrelation, adding 2 lags, and also with the white text we used larger confidence intervals and robust standard errors to take heteroscedasticity into account.
Okay, when we check the quantile.
So there is a symmetry in the quantile. Okay.
Yeah.
The log model.
Yeah.
Okay. So the scatter plot was better than the linear one.
It looks better, yes.
Yeah, and the scale of reference is smaller. And also we compared the adjusted R-square values, and it was close to 1 in logarithmic model. So we can say it's more convenient to use logarithmic when we compare it just with the linear model. And when we check the T ratio values to see if alpha and beta values are reliable or not. We see both constants are significantly high, so which means the estimations are very significant. When we check the normality, we reject the H0 because of the lower p-value we have. So we reject the H0, which is expected value of the residual is 0. Also for stability, we in CHOV test, we reject the p-value. So so the stability of parameters are rejected. For white test, p-value is 0.1, so we accepted homoscedasticity. And in autocorrelation, so it was positive, so we rejected H0, which is no autocorrelation. And then we tried to fix the model. Just with BG test, we got 0.75 as the p-value with 2 lags, so we had no more autocorrelation.
And then for the nonlinear model, basically always we had the Ramsey test, we couldn't get it specified, but then also again when we tried to fix it for the autocorrelation, we were able to fix it, adding the 2 lags. And again, for the white test, we could only take heteroscedasticity into account. Sorry. The Ramsey test, in this case, we fixed it, adding just 1 lag. So in this case, the model was well specified for us. And yeah, we also ran the F-test.
Okay, also we ran the F-test only for this model because we have 2 independent variables. So as a result, our p-value is very low, so we rejected the null hypothesis.
Then we have the first difference model. And here the Ramsey test is already specified. Also, for the stability test, for the CHOV test, there were no structural break because we did the COSUM test and we found a break in 1939 and we accepted H0. And I mean, so far this was one of the best models that we ran for the data that we have. Yeah.
Okay.
Okay, now we have time series models, and when we check the models, the moving average test, moving average model was the best for our data, as we can see from the table.
Yeah, and then we did the unit root testing, and these were the results that we had, and also there was in the stationarity testing we had problems with the GDP per capita, and that it said error. So we actually don't know why. So it was something that we wanted to ask you. I don't know if we can send you an email or you can say it to us like at the end of the presentation. And
yeah, the error is probably because if you put a trend,
yeah,
can you try inputting a trend?
Yeah. Oh wait, sorry.
So variable, unit root.
No, wait, no, it's.
No, you can do it from.
Yeah, it was the Capitanius.
Ah, it was the Capitanius. Okay.
Yeah. And
then we did it for GDP per capita.
Yeah,
we couldn't get a result. Yeah, it was.
Yeah, it was like, I mean, yeah.
Yeah.
Yeah,
Okay, go back.
Yeah, sorry.
Okay, where it says trimming parameter, do it instead of 0.1, do it 0.3.
Here? No.
No, trimming.
And okay. Yeah.
No, it's still
No,
0.1. Instead of
I know.
0.1, 0.3.
Like go back to the function packages.
No, sorry. sorry. Yeah.
0.1.
Ah,
Okay.
Okay.
Again. Again.
Okay, go back. Don't do it. Wait. Can you press the plus button next to the trimming parameter?
This.
No. Next to the trimming parameter.
This.
No. This one.
This.
Okay. Press cancel. Cancel. Okay. Trimming parameter. Put 0.2. Now press OK now. No. Do.
Yeah.
Yeah. I don't know. I don't know why this is happening.
I don't know if there was like from the data.
This is because in the beginning there is upward sloping. But for all the other variables, it's working. Yes.
Yeah, it's working. I mean, here with the chart, we just got the error in the GDP, but for all the others, we found the structural breaks. So.
.15. No. 0.15. No, there's nothing you can do. No.
Okay. Yeah, it was just also we ran the co-integration test, and everything was fine. And also the vector autoregressive models, we had all the different equations and the cat-balls too. And this is our presentation. We had that error, and that was the main thing. The thing that we wanted.
Okay. Thank you very much. The only thing you can do about the test is go try 0.16, 0.17.
Okay.
This is the only thing, but 0.16, 0.17. Okay.
Yeah.
Okay. Who is next? Sylvia. Sylvia, can you?
Yes.
Can you start, and please be careful with the time.
Okay, I have to share the screen. Do you hear me?
Yes, you can share the screen.
Okay. Okay. Oh, sorry. Spoil it.
Nice picture.
So we changed the country because we had Iceland at the beginning, but the number of observation was not enough. So we choose Ireland at the end. So we first presented this time series plot of the linear, logarithmic, and later on the first difference model. So what we noticed is that since Ireland is considered to be a developed country, we can say that we can notice the environmental Kuznets curve in the graph of the annual CO2 emission per capita. That means that if at the beginning to become richer, Ireland had to pollute more, at the end, while GDP kept increasing, CO2 emissions started to decrease over time. This is due to greener technologies, stricter rules on the environment, carbon leakage. For what it concerns the linear model graph, we chose to show the Aldrich-Prescott filter. And we can see like the trend with the red line, and the green line is the real trend observed. And we can notice that there are some drops related like to the financial crisis of 2008, but also before to the wars. Our data starts like with the Second World War, and then we have the logarithmic graph that is like follow the same path as the linear one, but the scale of reference is smaller. Then on the next slide, we have the first difference time series plot, and here, like if we compare the two graphs, here we can see the growth rate, while in the other just the linear trend. So here we can say that while in the other graph we could notice just by looking at graphically non-stationarity, here we can see that the observation crossed multiple times the mean. So like we can observe stationary variable, but this has to be tested further, like later on with the test that we did at the end. Then we presented the color XY plot, and from this graph we can better understand the environmental Kuznets curve. And just like by looking at the graph, we can see that the linear model will not specify that, like, would not be the best one that fits our observation, because the trend of our data is more like a curve and not like a straight line. So so we first presented that in the introduction before starting with the regression correlation, because correlation shows just if there is a link between the two variables, while regression try to understand which is the direction of that bond between the two variables. So here we found that there is a positive correlation from the data that we presented here between the two variables. So we can say that we can reject H0, and H0 is no correlation, so that there is correlation between the variables. Then we have the summary statistic that for now we did just for the linear and first difference data. And the mean is more influenced by outliers than the median. Then we have the linear model. So here we have the scatter plot, but just by looking at that, we can say that this model, like the data follow a curve path, not a straight line. So like the result that we had from the Ramsey test was like expected, because the model is not well specified by this. And the other test, so the one of autocorrelation, showed us positive autocorrelation. So we rejected the H0, which is no autocorrelation. For the white test, we also like rejected H0, that is homoscedasticity, because there is heteroscedasticity. And from the Ramsey test, it's not well specified. So we tried to fix it. Then there is the normality test. And here we rejected the H0, which is like that the expected value of the residual is equal to 0. And this at 5% level of significance, so residuals are not normal. And for the stability test, we performed the first that we didn't present now, but we have in our Word file, the COSUM test, and we found that a significant year was the year 2000, because it was related to the moment in which parameters became unstable. So by testing the Cho test, we noticed that the p-value is equal to 0. So parameters are not
The
stable
environmental Kuznets curve in this graph is clear. You can see the curve.
Yeah. It is clear. In fact, like the linear model cannot specify the Kuznets curve since like the values are following a curve trend. As I said before, like in all the graph we presented, the Kuznets curve was evident also like in the XY and the time series. And this is because Ireland, like at the end, from the 90s, started to kept becoming richer and richer, but started to pollute less. That's why of this environmental Kuznets curve. And then we fixed the linear model. So for the autocorrelation, we added one lag value of the independent variable, the GDP, and 3 dummies that are related to the significant year that we found. And to take into account heteroscedasticity, we added the robust standard error that made the confidence interval and the standard error to become larger, but we cannot get rid of heteroscedasticity. We just took it into account. And then for the Ramsey test also, we were able to fix it, adding one lag value. And so in this case, the model, by adding just one lag value of both variables, so GDP and CO2, got fixed, and the model in this way was well specified. And for the normality test also, we added one lag value of each variables, and we fixed the problem that we had. Then for the quantile regression, we presented the graph. And so the tau quantile regression graph and the quantile regression model. So for what it concerns the graph, the blue line is the average response, so the standard OLS, while the black line with the cross represents the quantile regression. And here we can see that the two lines are really close one to another. So actually there is not that much difference between quantile regression result and the linear OLS result. But quantile regression is useful because it can capture better the complexity of the model with respect to the OLS model, the linear OLS that we performed at the beginning. Then we present the same test. We did the same test with the logarithmic model. And here we found again, here this model, it is better, like describing our data than the linear model, but still, when we analyzed, we didn't report the result, but we analyzed also the adjusted R-square, and here the adjusted R-square had a higher power, a higher explanatory power with respect to the linear one, but still we had problems related to autocorrelation because there is also here positive autocorrelation, heteroscedasticity, and also the model through the Ramsey test is not well specified. And for what it concerns the normality test, again, the residuals are not normal. And for the Cho test and the QLR, again, for the Cho test, we chose the year 1985 because from the Kusum test, we found that to be like a year where values started to be unstable. And in fact, we found that in those years we reported the parameters, the values are unstable. And we tried to fix again also the logarithmic model. And we succeeded with autocorrelation, heteroscedasticity, we just took it into account, adding the robust standard error. And the same we did with Ramsey test. We had also here like one dummy variable, like related to significant year that we found, like the 1929, that was like important, maybe like related to the Wall Street crash of that year. And here we have done the linear model. Okay.
So this looks to be a very good fit, this one.
Yeah, this is really one of the best we found, not the best.
Okay. For the nonlinear model, we can consider the regression line, and here we can observe that the fitting is better since it approaches the curve shape, and it's also R square show that.
In fact, the adjusted, if we look to the adjusted R square, is equal to 0.9224415, and so the explanatory power is has increased. So we can observe that the two variables are statistically significant because we have proved that thanks to the significant approach and the confidence and the confidence interval approach. And from the CUSUM, again, we can observe that we found stability. So we decided to run the CHO test. Sorry, I have to.
Yes.
Okay. So the CHO test for the year 1939 and the QLR test with a 90-50-75, sorry, and we reject in the first case we don't reject H0, so we consider the stability of the parameters, and in the second case we reject H0, we rejected H0, sorry. Then we have the white test, and we can observe that there is heteroscedasticity. And for the autocorrelation, we have the two same tests. So for the Darwin test, we have positive autocorrelation, and for the Birch-Godfrey test, we have autocorrelation too. In this case, the H0 is no autocorrelation, so we reject it. Okay. Okay, and the normality test for the alpha at 5%, sorry, we rejected H0. Okay. So then we fix in the nonlinear model, and we can observe that the autocorrelation have for the Birch-Godfrey test have a p-value near to 0. So we add the one lag value of CO2 and one dummy variables. So for the Ramsey test, we add the one lag variable of the dependent variables too, and the p-value is 0.85 and so on. So we don't reject H0. So the model now is specified, and then we have the normality test, and in this case we don't reject H0 too, and so we can consider that the residual are normal now. Okay, then we pass to the F test. Here we consider H0, and yes, H0 says that beta 1 and beta 2 are simultaneously 0. So the p-value is very near to close to 0. So we are rejecting H0. And then we pass to the first difference model. Okay, in this case, the graph shows that our model tries to explain that the growth rate of the variables. The model tries to explain the growth rate of the variables, while, as we've seen before, the linear OLS was just explaining the general trend. And in this case, the first different model is not helpful in the long run because we will see that all the growth rate will become 0 or close to 0. So we can analyze this graph from CO2 and GDP point of view, and we can observe that they not fluctuate around a constant mean. So we can say that they are not stationary. What else? Yeah, okay. But on the other hand, we can observe that the graph about the logs first difference of CO2 and GDP. So we have seen before. We have in this case, if we consider the green line, in both cases the multiple times the mean value 0. So we can say that the two variables that we are studying now are stationary. So with this first different transformation, we turn to the two non-stationary variables that are CO2 and GDP into stationary variables, and we will investigate in the future this part. So okay, for the from the CUSUM 2 now we found stability, so we decided to run the CHO test that we have in the other slide. Yes, for the year 1939.
You have one minute left.
Okay, I will run. Okay, so we can read that. And for the QLR, and then we have the white test when we reject it 0, and the autocorrelation when we reject it another time. Then we fix in the first difference model, and when we can observe that there is no autocorrelation and that is heteroscedasticity. And then we study.
You did the time series, okay?
Okay, time series model, exactly, okay. And unit root test with all
ADF,
the
not
okay.
ADS, ADF. On the top, it says ADS.
Sorry,
ADF.
sorry, yes, it's a typo, sorry.
ADF, next, Capetanius, okay, you found it, non-convertible matrix, okay.
Yeah, we found a mistake while performing this. As the previous group, in the same way, we found like a problem, but we tried to change it like from 0.1 to other values, but it was like always the same results we had.
Yeah, there is probably
just
nothing.
For GDP, because for the other variable, we found it like we found the result just for GDP per capita in the linear way, like the other.
Yeah, the other thing you can do is add more lags, maximum number of lags. Instead of 1, make it 2 lags.
Okay, okay.
Okay.
Okay, then we see the co-integration text with Engel Granger. So we explain all the steps that we have done. Go on, maybe.
Okay.
Okay.
And then you did the Granger causality.
Mm-hmm. Okay.
And you did the Granger causality here. Okay, the var, the lags.
Yeah.
Okay, very good.
Exactly.
The next slide.
The next slide is another
Granger causality.
equation.
This is called Granger causality. Ah, you did the Ketvans as well.
Sorry, excuse me. Yeah, the first question is the second one. And then we put a graph of the chaos for time varying, and in the future, well, we found data about energy consumption, but we will add to make the model better in the final presentation.
This is a very nice graph, the last one. Okay. Very good presentation. Very good.
Thank you.
Very good work. Very good work. Sylvia? Is Sylvia ready?
No, I am.
No, who is next? Ah, it's not Sylvia.
No.
Ah, who is next?
I don't know. Thank you very much.
Thank you very much, Sylvia.
Bye.
Thank you. Who is next? After Sylvia. Who is presenting next? Is there somebody? Yes.
Sorry, I think that Dia Guluzade was supposed to present now.
Yes, but it's okay. The next one.
Viola.
Viola, you're the next one.
Yes, so we can present if he's not online.
I think someone wrote in the chat. I don't know if it's him, but otherwise we can do.
Reza.
Ah, yeah, Reza Razivand.
Yes. Can you start?
We are at 6:30, so I think it's our turn. Anyway. Okay, we will start.
Viola, if it's your 6:30, then it's better if you start. Okay.
Yes. Okay. Can you see my?
Yes, and then Reza after you. Yeah, please just be careful with the time, please.
Okay.
15 minutes.
Okay. I'll start. Hi everyone. We picked Canada. Canada because it's a G7 country. It's a developed country and it's a global leader in renewable energy and clean energy. And as we can see, we tried to perform OLS for the linear model statistically, the regression was statistically significant for the linear model. GDP, in fact, is statistically significant at 1%. And then we see the scatter plot. Next slide. Okay. The regression line is the orange one, and then we see our observation, the green one, and we can see that there is a shape that looks like a curve. Okay.
Sorry, I think it's better if I use this one.
Okay. So the observation are the green one, and then we can see that as Canada became rich, CO2 flattened after a peak, and then start to decline again when new technologies, green innovation, and higher efficiency in production, maybe outsourcing, were taking place. And then we can see the time series plot. So over time, the trend of our variable, annual CO2 emission and GDP, and we can see the correlation matrix that is strongly positive as 0.8. So as GDP per capita grows, CO2 does the same thing in the linear one. And then we can see the color XY plot and the summary statistic, which is a nicer representation of our curve. And here we can see our three models, the linear, the non-linear, where we squared our GDP per capita variable, and the logarithmic model that we're going to talk about. The log of GDP is still statistically significant at 1%, and the adjusted R-square is a little lower, as it is 70%. And we can see the graphs, the scatter plot, and we can still see the shape like a curve of our observation compared to the one in the linear model. It's like a curve. And then we can see again the time series plot for the log model and the correlation matrix. Still the trend, they're similar. And they, in fact, they are strongly statistically significant as with a correlation, positive correlation. And we can see also the color XY plot and the summary statistic of the logarithmic model. And then the nonlinear model, we see that it's statistically significant again with our variable that is square now. And then the environmental coordinate curve, which is what we are trying to analyze here. And we can see that as the country becomes richer and richer, CO2 tend to increase. But in the middle of the growth, we can see the pollution that is constant, and then a decline with the new technologies and higher efficiency probably. In the same time, GDP keep growing. Here we can see the time series plot over time and the color XY of our non-linear. Okay. And then we performed the F-test, the test statistic for the non-linear model, to try to test if our variables were zero simultaneously, but we reject the null, and beta 1 and beta 2 were not simultaneously zero. Here we can see the actual vs fitted data. This graph, it's still, we can see our curve for the log model and the nonlinear model. And then we performed the residual plot to try to identify some outliers to then remedy with dummies later on that my colleague is going to explain. And we tried, in fact, to test for dummies, and we found at 10% 1972, and at in the 2017 at 5% level of significance. Then we did the quanti-regression. That is a regression that is trying to look at some specific ranges. So when CO2 is relatively low, in the middle, or relatively high. And we see from the graph that the blue line is our OLS estimator, and the black line are the follow the quantiles, and we can see that the last one is outside the confidence intervals. But then, performing robust standard errors, we improved our graph. So we saw how CO2 emission responded to GDP per capita, considering potential heteroscedasticity. And here we can see a comparison between QR with logs and OLS with logs. And it is interesting because we can see that with OLS, so the average response, if the log of GDP increased by 1%, the log of CO2 increased by 95. While if we consider QR, quantile regression, we can see that an increase in a relatively poor country of 1% in GDP increase, CO2 increased by 129%. While for CO2 emission, when are relatively high, so a country is rich, if GDP increased by 1, CO2 increased by 43. So basically, we can see from this test, from this regression, that CO2 emissions increase more when a country is poor and increase less when a country is rich. So basically, they pollute more because maybe they use less efficient production techniques. With this graph of the QR with logs, I leave the ground to my colleague Viola.
Okay, then we tested the linear model. And so about the normality test, we can say that we reject the H0 hypothesis. So residuals are not normally distributed, but then there is heteroscedasticity and also autocorrelation. So then we solved autocorrelation and heteroscedasticity. In heteroscedasticity, we updated the standard errors, which are higher now in the value. And then we included a lag of annual CO2 emissions and dummies, which are 1972 and 2017 for autocorrelation. And then we solved autocorrelation as the p-value is 0.17. And then we tested the linear model, and the same, the residuals are not normally distributed, there is a heteroscedasticity, and there is autocorrelation. We did the same for the nonlinear model, and we solved the heteroscedasticity and even autocorrelation. And then we tested for the logarithmic model as well, and we got the same results. So we had to fix heteroscedasticity and autocorrelation here. And actually here we have a question about, Professor, about autocorrelation, because we use dummies for the logarithmic model that we got from the linear model. And probably actually here we had to use dummies by checking the residuals plot from the logarithmic model.
That should be very similar.
Okay. Yeah.
The dummies from the linear and the dummies with the logarithmic should be very similar.
Okay. Anyway, we solved here autocorrelation as well. Next slide for this first difference model, and here the only statistically significant variable is the GDP per capita, the growth rate of GDP per capita at 1%. Here we compared the linear model time series plot with the first difference model time series plot, and here we can see that the first two graphs show stationary non-stationary variables, and on the other hand, growth rate of annual CO2 and growth rate of GDP are stationary variables. Then we did the graph, the scatter plot graph, and the summary statistics here as well. And then we tested for first difference model, but in this case, residuals were not normally distributed, and there were no heteroscedasticity, neither autocorrelation. But actually, this was in contrast, I guess, with autocorrelation. I mean, here we see that there is no autocorrelation, but then we run the Darwin-Watson statistic, and it seems that there is. I don't know if you can help us somehow.
The null hypothesis is
Here?
that have you done well, you've done the Darwin-Watson, but have you done a Bross-Godfrey test?
Yes, also.
Yes. There's no autocorrelation, so you cannot reject. So the Bross-Godfrey is more powerful than Darwin-Watson.
Okay, so better
So
to
you should
check
keep the result.
Okay, thank you. And then we run also the reset test. The only one we do not reject is the first difference model, which therefore could be a more realistic model for Canada compared to the other, linear, non-linear, and logarithmic. Then we run the QSUM, CHO, and QLR, and as you can see from the QSUM test, we get that probably there was a break in 1958. So then we run CHO test for 1958, and also QLR test for, and from the QLR test, we got that probably there was a break also in 1940. We did the same for the nonlinear model and the logarithmic model and the first difference model. I just want to go on because I have other questions. And then we tested, we checked forecasting. I don't know why you can't see the slides. Okay. And no, you can't see the graphs, right?
No, but I can see them on the left.
Okay.
The small graphs, they are okay.
Okay. Probably here you can see.
If you press refresh them, because it's from the web page.
Yeah.
If you refresh the page, it might
see.
work.
Maybe here. Okay. Maybe now. Okay. And okay, thank you. Here, this is like 41. Okay. Here, I wanted to ask you if it's okay, like that only the first autocorrelation is significant at 1% level.
Yeah,
okay.
yeah.
Makes sense, right? Once remove the effects of the years in between in PACF. Because, I mean, it's okay.
No, this is what you would expect.
Okay, thank you. Then from this, we also try to forecast in the first different model. And by looking at the ACF, we can claim that the 15th and 16th autocorrelations are statistically significant. So on average, yesterday is affecting today. And from the PACF, the third autocorrelation is significant at 10% level, the 15th at 5%, and the 16th significant at 10%. So on average, the correlation between the third lag, so 3 years ago, and the 16th lag 16 years ago is 13%. And once removed the effects of the years in between, otherwise it will be 16%. Then we ran the moving average model as well, and we had to drop one observation. So we changed from 1871 to 2018. 2018 to 1871 to 2017, to check. We set to 2017 to forecast what is happening in 2018. So we then estimate the MAE model and forecast what is happening in 2018. And the coefficient of CO2 emissions growth rate is 0.008320. And that is what has happened in 2018. And then the coefficient of CO2 emissions growth rate is 0.028910. That is the forecast. Then we also ran the moving average model, and we compared it with the autoregressive process and a mixed autoregressive moving average model. And we can say that the MA model is the best one to use for forecasting because it has the lowest Kaiki criterion. And then we also tested the stationarity. and we were supposed to find non-stationarity for GDP and RSU2. This is what happened, and so we can say that the the linear model is a spurious regression. But then, when we run the same test for the first different model, actually here the p-value, this is another question for you, Professor, is 0.053. And if we reject, if we don't reject.
I cannot see it because it's too small, but.
Sorry.
It's okay, it's okay.
Like this. Maybe you can see now. If we reject at 5% level, then if we don't reject, then the variable is non-stationary, which doesn't make sense because it's the growth rate. It's supposed to be stationary.
Yeah, so you can say what happens at the 10%.
Okay, yeah, this was my question. Perfect, because then is in contrast also with the test, with the co-integration test. And in the first step, we figured out that it was stationary. So, okay, I was wondering how to fix it. Okay, thank you. Then, and we got the same results for the Philip-Perron test, but here also the annual CO2 is non-stationary. I mean the growth rate.
Yeah, the growth rate should be stationary.
Okay, but here, I don't know, the result was
that... this is with this Phillips-Perron.
So it's okay?
Yeah, you can write that Phillips-Perron disagrees, but
then we keep this one as result. Okay.
You present all the results though.
Okay, perfect. Then we tested for co-integration. Logarithmic model, has no co-integration. The linear model as well. The first difference model. Okay, this was related to my question about the growth rate of annual CO2 emissions, stationarity or not, and you already answered. And here there is co-integration. And then we also run the vector autoregressive model. And here the information criteria tells us that the Schwarz chooses 2 lags, while Akaiki chooses 3 lags. And if we go with Akaiki, we do again the model, and we get 2 equations. The first one of CO2 emissions and 2 lags of CO2 emissions and 2 lags of GDP. And the second one of GDP emissions with 2 lags of CO2 and 2 lags of GDP. And actually, this is the last slide.
Okay, so you've done Granger-Causality, you've done co-integration. Okay, the only thing you have done from what we've seen is Ketvals, but you don't need to do it. You can try.
Yeah, I mean, we still have.
And I don't remember if you've done the filters in the beginning.
No, we didn't.
Okay.
Yeah, so you can do the filters as well.
Okay.
Okay.
Perfect.
Okay. Thanks for this. Who is next?
Thank you.
Thank you.
Reza is next.
Hello.
Yes, Reza. Can you please keep a note of the time? 15 minutes.
Okay.
So please do not. Please be aware of the time. So if you could try and present on time, that would be great.
Can you see me or
I can see everything. Yes.
Yeah. First of all, I apologize because of Mehrdad is absent. I guess he left a message, left an email for you.
Dio buono, io sono andato proprio, guardavo solamente il PowerPoint, anch'io, guardavo solamente il PowerPoint, non vedevo, infatti.
Okay, we can hear you, Reza.
Yes,
Reza, we can hear you.
Apologize.
Let's go to the presentation because we don't have much time.
Okay. First of all, I want to talk about
Viola. Okay, Reza, go on. Let's move from the summary statistics.
Yes, and as you can see in this table, we can notice that GDP per capita has a much bigger scale than CO2 emissions per capita, but this difference is mitigated when using the log of the variables. The mean and median are different, especially for GDP per capita, which means that the data are not symmetric. We check the correlation between CO2 emissions and GDP per capita, and this is positive, and correlation is statistically significant. Furthermore, it implies that if the Netherlands become richer, CO2 emissions per capita increase, and this country become more polluted. And the correlation between the variables are significant because the p-value is 0, and we reject the null hypothesis of no correlation. And since the correlation between two variables does not imply causality, we need to move further with our analysis and estimate regression. As you can see in my the linear and the two variables grew together until the end of the 30s, and then as the Netherlands become richer, it seems that this country use better technology to produce less CO2 emissions. We highlight some years in the graph, and this is the first one is the first World War, and the second one is the second World War, and the third one is Cold War, I guess. This is time series plot of a log of GDP per capita and log of CO2 emissions per capita, and color XY plot, and this is the same with the previous model. And the graph shows that CO2 had a more rapid growth until the beginning of the 1960s. Then GPT started increasing faster than CO2.
Reza, can you please go to the models? Can you please go to the models, because we don't have time. Let's go to the models. Okay, this is the linear model.
This is the first.
Let's go. Let's go to
linear model.
Okay.
And,
okay. Let's go to the log. Let's go to the log model.
Log model.
This is the nonlinear model. Very good.
Yeah.
The dummies. Okay, let's see the log model. Okay, very good.
This is the linear logarithmic model, and as you can see, the coefficients are significant, and the linear logarithmic model and the linear model are are the same, and as you can see, autocorrelation, the p-value of autocorrelation is near to 0. So we had to reject null hypothesis, and heteroscedasticity is again we have to reject white test. So we have to improve our model with add lags and robust standard errors, and you can see that again all coefficients are significant, but we can't solve the normality of residual again, and we have to again add some dummies and robust standard errors. as you can see, we add some dummies, and all coefficients are significant. And again, the normality of residual are not solved again, and we can see that is again in zero, near to zero. This is the result of a linear logarithmic model, and we can see that the whole result of the different models we run in this model. The first difference model, and we run this model, and as you can see, and the constants not significant, but GDP per capita, growth rate of GDP per capita is actually significant. And we run autocorrelation and heteroscedasticity for this. And as you can see, we solved the heteroscedasticity, but the autocorrelation is remain not solved. So we add lags. When run the model, we find out the first lags of GDP and CO2 emissions are not significant. So we decide to remove them from our estimation and add the second lag of CO2 emissions, as you can see in this model. So in this these coefficients are significant. About reset tests for specification, p-value was about 0.54, and autocorrelation was not solved with p-value near to 0. Test for normality of residual was not satisfying, so we decided to add dummies to our model. In this model, we add some dummies.
Can we go to the end,
Reza,
because we don't have time. Is it possible to go to the next model, to the last one? Okay, this is the first differences. Okay.
This is the result of difference
the
model?
First differences. Yes.
Yeah. This is the quantum regression. And the quantum regression helps us to see the detailed behavior, which means how to coefficient change when the dependent variable is related low or high. We need quantum regression in order to investigate whether low CO2 emissions are different from high CO2 emission per capita. And we also computed the quantum regression with tau 1.5. And the residual are not normally distributed. We can notice that the coefficient is very similar to coefficient of the regression of the original linear model in this model. We run the model for quantum regression in linear logarithmic model, and as you can see, CO2 emissions are affected by GBT only when CO2 emissions are relatively low, as we can see in this graph. When the constraint becomes rich, it looks like CO2 emissions are not affected by GDP. Time series models. When we run these models and we find out the ARMA with one average regression and moving average 1 is the best model because it minimizes the information in criteria.
Okay.
And this is the forecasting table of log differences.
The next one.
Stationary and unit test.
Okay, can I see the tests?
Yes.
Okay,
this
this
is
is the test,
the
Dickey
test.
Fuller, KPSS. Okay, everything is fine.
Yeah, and Capitanius. And
you did the
filter
filter.
data.
You did the filter. Okay, very good.
Yeah.
And
co-integration for this.
Okay, there is no
And,
co-integration. There is no co-integration. Did you do Granger causality?
Yeah. Now I have a question and for this model. And the first one in the logarithmic annual CO2 emissions, the p-value is about 0. We reject non-stationary.
Yeah. So this seems to say that the annual CO2 emissions, when you take the logs, are stationary.
Okay. And the result is there is a co-integration between CO2 emission and GDP per capita because p-value is less than 5%.
Okay.
This is a causality test, equation 1 and equation 2, and this is the forecasting for vector regressive models.
Okay. That's it.
Thank you.
Thank you very much. There is a very good presentation. Okay. Who is next? Denise. Denise.
Hello.
Hello,
Me and
Denise.
Gisem. Yeah, hi.
Hi. Can you start and
Yep, just 1 second.
try to be on time, please?
There it is. Can you see it?
Yeah, I can see Belgium, yes.
Okay, yeah, so me and Gisem are gonna talk about Belgium. We decided to write about this country because it's one of the more developed countries and it was gonna be like a good example to show how the environmental Kuznets curve is gonna be, a bit more prominent. So here you can see, actually, wait a second, let me just make it a bit bigger. Yeah, so here you can see how the environmental Kuznets curve starts. Then only here for just like, I think 5 years, there's in times, as you can see, and somewhere around here, this line, the GDP line process.
Can you be closer to the microphone so we can hear you?
I'm sorry, can you hear me? Can you hear me now better?
Yeah, I can hear you, yes.
Okay, so yes, this is basically about the environmental Kuznets curve. And now the models, we did the linear model, which actually this model, the GDP per capita variable is not significant enough. And after that, we plotted some tests, but I'm gonna show you this later. Now the nonlinear model, everything is significant. If you look at even the R squared, it's fairly high, 56% of the input variables explain the output ones. Then the logarithmic model as well, it's you can see here both of them are significant. Again, R squared, this time it's not that high, only 10% explain for the variations. First difference model, again, it's significant, a bit more higher R squared. After that, we have the linear model. Now the tests for the linear model, there is autocorrelation, fortunately. Heteroscedasticity is not present here. We can not reject the null hypothesis. Then here for the reset tests, we reject it. And yes, basically there are some misspecifications here. For the test normality, we can see again over here that it's above the 5% threshold. So we reject also the normality test. And we did a CHALT test, which again rejects the null hypothesis. So there are actually some structural breaks, which can be due to that 5-year gap that we showed at the beginning from 1980s to 1985s, where there was an economic crisis. So now for the nonlinear model, the nonlinear model, you can see that there is a autocorrelation. Sorry, my mouse is not showing up. There is autocorrelation. We cannot. Sorry, we reject the null hypothesis. Here again, we reject the null hypothesis, and there is heteroscedasticity. Again, we have misspecifications, and this time we reject the null, and yeah, for this thing, the errors are not normally distributed. And yes, again, the CHALT test has structural breaks. So basically, for the nonlinear model, everything is rejected, every null hypothesis. Now, how we fixed the nonlinear model? We fixed it by adding the logs of the dependent variable plus dummy variable. I think we added 1982 as a dummy variable, and yes, I'm not really sure if we did that correctly, because we got a bit more high results here for example, for the White's test for heteroscedasticity.
Why you're not sure?
I don't know, because they seem a bit too high for me, but
yeah, but these are the results. So
yes, it's still above the 5% threshold, so it should be fine,
so
right?
It should be fine, yes.
Okay then, all right. So that was my only concern, that I just thought that they were a bit too high, but anyways, yes, you managed to fix all of them. Only for the Charles test, we couldn't fix it here. It's still under 5%. Logarithmic model. Yep, now logarithmic model. Again, I think everything is rejected here. Yep, the autocorrelation is present, heteroscedasticity is present, misspecification, we have misspecification, the errors are not normally distributed, and we have structural breaks. And we did the same with the logarithmic model as we did with the nonlinear one. And I think we managed to fix everything except the CHALT test again. After that, we have the first difference model. Here, the autocorrelation is present, even though we have like 0.0 some points to reach the 5% threshold. Again, the heteroscedasticity is present. Here, the misspecification tests is not rejected, so the null hypothesis is not rejected. So the specification is adequate. Then the normality of residuals is rejected again, and the CHALT test, on the other hand, is not rejected. The null hypothesis for the CHALT test. And we fixed it again by adding logs of the dependent variable and dummy variable. I think here we managed to fix everything. Yep. And after that, we did the autoregressive models, the moving average models, and them both combined. I'm a bit confused for those as well, because for the autoregressive one, the constant is not significant.
Yeah. So in this case, you should collect the Akaike information criteria, create a table, and see which model minimizes the Akaike information criteria.
All right. We haven't reached that point yet for the Akaike.
You might have seen You might have seen the previous presentations doing this.
Yeah, I sold them all. So that's the best option for me to do, because even here in the combined one, nothing is significant enough. So yeah, I'm just gonna look at the previous presentations again one more time. This is about the time series, and now the unit tests. Here, I think, yep, as you can see from the p-value, we reject the null hypothesis, so we have some stationarity, both for the normal variables and the first difference variables. Then we did key PSS tests, which both here and here for the first differences for the CO2 emissions and first differences of GDP. You can see that both of them don't reach the 5% threshold. So again, we reject the null, and we can conclude as well that there is some stationarity. And same again with the Phillips-Piran tests. Although here again, we don't have significance for the constant, so I'm not sure how to interpret that. Here we have significance for both of them. So again, we reject it, and there is stationarity. But for the CO2 emission, the first difference of CO2 emissions, there isn't here any significance in the constant. Is that going to be a problem?
No.
No? Okay. Okay, then so we reject it again, and we have stationarity. We can conclude that we have stationarity as well.
Yeah. So you need to do co-integration, Granger causality. Yes?
Yes.
What else you need to do?
We have a lot more to do. We have the...
You've done the filters? No?
We have the quantile regression. We haven't done the quantile regression as well.
The quantile regression, the filters?
The filters, yes.
Granger causality, co-integration.
Yes.
And unit roots.
Yeah, we did the...
Unit roots
yes,
you
and
did,
the
unit roots you did, but you didn't do the Capitanius, no?
Yes, I didn't do the Capitanius. For some reason, I couldn't install it on my computer, but I think I'll have to just reinstall Gretel. And
Yeah, maybe you need a newer Gretel.
yes, so that's why I
Okay.
didn't do the Capitanius.
Okay, very good work.
Thank you.
Okay, thanks to everybody. And then we're going to meet, I think, next Friday. If you have any questions, you let me know next Friday. Any more questions? Anything, anybody wants to ask something? Anybody wants to ask?
Professor. I cannot interpret the color XY plot of growth rate of GDP and CO2 emission. Is it possible to help me how to interpret this plot?
Yeah, if you show me doing, I can. Although this is something, yes, you should do this on your own, but you can share it to me. I can have a look. Can you share the screen?
Yes.
Okay, so but you need this one. Yeah, but this one it says that these are the first the logs.
Yes.
These are the log differences. Yes, you don't need to say too many things about the log differences. It's the color XY plot is mainly for the levels and the logs, not for the differences. So here what you're saying is that most of the observations in the 19th century are very close to zero, but as you are moving to the 20th century, then you're getting deviations from zero for both of them.
Thank you.
Okay.
And is it possible to send your correct email because I don't have your email to send you a message.
If you go to the presentation, you have my email there.
Okay, okay, thank you.
Okay. Any more questions?
Yeah, Prof. I have wrote to you before asking for mates. Okay, so at the end of the lesson. Okay.
Yeah. No,
okay.
You can ask now.
Okay, perfect. So I can share the screen, so I can.
I can make you presenter. I made you presenter.
Okay, perfect. Okay. Sorry for there is a lot of. So my first answer, the question was about the VAR, because we have done the VAR selection here, and if you know the AKI criterion suggests to use 5 lags, while this bars suggests to use 3 lags. I have done
This is for the VAR. You should go with the Schwarz.
Okay, so with the Schwarz, not with the Akaiki, because if I do with the Akaiki,
you can do both. You can do both. Both of them are correct.
Yes, because if I do with the Akaiki, it results that the GDP Granger cause CO2. But if I go with the Schwarz, it emerged that there is no causality in this case. So I was thinking that maybe it's because I can interpret it saying since the Schwarz suggests less lag, maybe it's saying that if I consider 3 lag, so the GDP of 3 periods ago, these are not significant, but the GDP of five periods ago, these are significant. This could be an interpretation.
No, but are you comparing the p-value with the p-value from the F? These are 2 different things.
Yeah,
the F test tells you the 0.19 you have there tells you whether all of them together are significant, and at the 19% they are not significant.
Okay.
So this is a joint test.
Okay.
The ones you're highlighting on top are individual tests. The one that you're highlighting is a joint test. So these are 2 different things.
So I should report both the VAR.
You report everything, but you need to focus on the joint test, as we said in the class.
Yes, okay. And so I should consider the Schwarz in this case, but I can report also the VAR with the lags of the Akaiki. It's not, it's the same.
Both of them are correct.
Okay, okay. Also, if they give different results. So it's also if one gives causality and with the other give no causality.
Yeah, that's an interesting thing to report and comment on.
Okay. And another problem is that for the forecast, I managed to do the forecast for the moving average model, but with the autoregressive model, I have a problem because if I remember well from your lessons, to the forecast, I have to set range and drop an observation. And then,
yes, you have to drop one observation for if you want to make a forecast.
But for the annual CO2 or the growth rate from there?
No, if you do it from the sample, it is done for both.
Okay, for both, also for the okay.
No,
perfect.
if you do it from the sample, Gretel does it for both.
Okay, perfect. And then I go to model yeah, and I click. Okay, it's already. But when I go to analysis and I click forecast, it gives me there are no observation available for forecasting out of sample. You can add some observation now if you wish.
Sorry?
When I click on analysis, sorry, where is So when I click on analysis and I click forecast, the problem is that it gave me this result, but I have rated the sample.
Number of observers to add 1.
Okay, so I had 1 observation. Okay, perfect. Okay, so and then it for 2009.
And then you do, yes, 2019, yes.
Okay, so not 2020. So, no, 2020. Okay.
From 2019 to 2020, you can do this as well.
Okay.
Okay.
Yes, and the last question, and then I have finished. It's about yes, dear. I've tried to for the first difference model, it emerged that there is no correlation. If I do the Brout-Goffrey test and the Darwin-Watson test, there is no correlation. But if I do the residual correlogram, there is correlation, because basically
if you focus on Bross-Godfrey.
Okay, so I can report the correlogram, but basically science
I can say that the Bross-Godfrey is the most powerful test.
Okay, perfect. Okay, so I'm done. This was my question, basically.
Okay, very good. Thank you. Any more questions, or shall we meet next Friday? Any more questions? Okay, so we are meeting next Friday then. Okay, good night to everybody.
Thank you, bye.
Bye-bye.
Thank you, bye.
Bye, thank you.